Sorry for that. I'm a PowerPoint user, obviously. So can everybody see the screen okay? Yeah. Frequently asked questions, brought to you by the researchers at the Perceiving Systems Department and Naureen, former member. All right. The first one, you've already seen it now a couple of times. Most important thing, check out the wiki and it will fill that in. So now, first up, there's a lot of confusion about converting between simple, Simplex, and maybe star. Simple and Simplex sound the same, right? They both have thetas, they both have betas. Can't I just take simple betas and plug them into Simplex and vice versa? Vasilis, can I do that?
No, you should not do that. So the models are trained from scratch. They don't share the shape space. So if you have one body described by, let's say, 10 betas in simple, these 10 betas represent a different body in Simplex. And also this doesn't hold just for shape, this also holds for pose. So let's assume that you found a magical way of guessing the beta values of simple and Simplex, like in the image here. So you have your orange mesh of simple, you have the exact same shape in blue. And you'll say, okay, I want to save time, I'll just copy the simple parameters in the Simplex, I should get the same mesh, right? You will actually won't get the same mesh. And the reason for that is, as I said before, the models have been retrained. So the joint, like the template is different, the joint regressor is different. So what happens is that when you try to pose a Simplex body with a simple pose, the centers of rotations represented by the joints are different, and you get the image in the middle. Like your meshes do not match. So what you need to do is to transfer simple to an intermediate simple mesh represented in Simplex topology, and then fit Simplex to that mesh, to recover the correct parameters.
Before we go on, let me point out how dangerous this is, because you know that they look pretty similar, right? They're close, the poses. They're close enough that you might not notice that you're doing the wrong thing. And then you're going to go and evaluate accuracy or something on some benchmark, and you're going to get a really bad result because you did the wrong thing. But they're dangerously similar, and that is why we want to emphasize this.
So how do we do it? So first of all, like simple and Simplex don't share the same topology, so we need to find a way to transfer between the models. If you have simple H and star, perfect. They share exactly the same triangulation, so you can the vertices map one-to-one. For simple and Simplex, what we do is that we register the two meshes, so we bring them so that we use non-rigid alignment to bring them to correspondence, and then for every point on Simplex mesh, we find its nearest neighbors on simple and store the index of the triangle and the barycentrics. So from this, we have a mapping. From every simple mesh, we can use the barycentric interpolation to compute a mesh in Simplex topology. So now that we have this default mesh, what we need to do is to fit Simplex to the target, to this mesh. The way we do it is we solve this problem with the iterative optimization. So we optimize for pose and shape parameters of Simplex, let's say in this case, and we try to minimize two objectives. These objectives are one, a loss on the edges. So what we mean is we penalize the vertex pairs that form an edge on the mesh, and also the actual vertex positions. This is done, although it might sound redundant, I have vertex positions wide away the edges. This helps converge to a better minimum and get a tighter fit.
And there's code.
Yeah, we have code available, and feel free to ask any questions you might want about this.
Yeah, are there any questions? I can't see the chat anymore, so if somebody else is checking, that would be great.
Not yet.
Okay.
Oh, there is one just came in.
Right.
What about simple 10 and simple 300? Does simple 10 have the first 10 principal components of simple 300? Yes.
Yes, indeed. It's a great question because the next question is very similar. So I want to use a mass. It's a data set where everything's in simple H format, but I only want simple parameters because that's all I care about. How do I get these? Well, simple H is exactly simple with the addition of the articulated hands. And so you can basically ignore all of the parameters having to do with the hands and you'll get the simple model. That is, the first 21 joints in simple and simple H are identical. So you just take the first 21 times 3 numbers in the theta parameters vector, and that's it. You've ignored the hands. Now, if you want to convert a mass to simple X, you're going to need to use Vasilius's code he just talked about to transfer. But we are planning to provide a version of a mass in simple X format. The reason we didn't do it was because most of the data sets don't contain hands or face motions, but we're starting to get more of those data sets in, so it makes sense to do it. Any questions on that?
There are no questions.
All right. So you probably see in papers this complicated thing, MPJPE, for evaluating accuracy of 3D body shape and pose methods. And PA stands for Procrustes Alignment. So why would anyone do this? So what is going on here? Well, most of the methods that estimate, regress, or optimize body shape and pose do so in the camera coordinate frame, not in the world coordinates. So the problem with this is most of your ground truth happens to be in world coordinates. And so you need to bring this body, which isn't in world coordinates, into some sort of correspondence with the ground truth. And in many of the methods we see working on real images, the body comes out kind of tilted. Sometimes it's flipped left to right if it makes a mistake, it's ambiguous. And people don't like this because they see that they mostly got the pose right, but they get some high errors on MPJPE, which stands for mean per joint position error, which is computed over all the joints in the body. So it's kind of the obvious distance between ground truth and the body joints. Now, but even MPJPE does something a little funny, which is that because most people assume an orthographic camera or scaled orthographic camera, weak perspective model, and they don't calculate the real depth of the person, and it's ambiguous anyway in a single image because there's a scale ambiguity. People translate, the standard thing for MPJPE is you translate your result to the true root joint, i.e. the pelvis of the ground truth body. So this translation doesn't get rid of rotation. So here's a few examples. So these are bodies estimated in the Agora data set versus the ground truth. And the blue are the estimated bodies and the pink are the ground truth. And on the leftmost, you see the pelvis aligned case, which you use with MPJPE. And you can see that there's a scale and a rotation problem, which is resolved a bit by Procrustes. And you can see the error with Procrustes alignment is going to be much lower. Now look at the next case on the right. The left of the two right images suggests that this method totally flipped the body. It got left and right wrong. And of course, you'd pay a super high penalty for this. The error, it's a big error. But if you do Procrustes alignment, it actually solves for the rotation of the body, and the error doesn't actually look too bad. You get actually a relatively low error in this case. And this is why I think Procrustes alignment is a bad thing, even though we have done it many times in the past, and it's a standard thing to do, because it removes translation scale and rotation between the estimated body and the ground truth. Now, the good thing about this is it allows you to really focus in on pose. Am I getting the pose right? But honestly, if your body is flipped 180 degrees, who cares? You're not getting the pose right anyway. You're just lucky if it turns out to be close. So I think it hides a lot of sins, and the field should just phase it out, in my opinion. It's a crutch, and we should be trying to estimate bodies in the world coordinate system and we should stretch ourselves to do that. So that's my opinion. Any questions about PA, MPJPE?
There are no questions in the chat.
Are there any verbal questions so far? All right, moving on. People use joint regressors for all kinds of things. What is this joint regressor business? So aren't joints joints? And why do different data sets need different regressors? Well, here's the thing. On the left, you've got a simple body model, and those are the joints for that model. Look at the hip joints. So those hip joints are placed roughly where the centers of rotation of the hips would be. And then look at on the right, a COCO image labeled by a human. And where's the human put the hips? They tend to put the hips way out. So if you ask a human where are your hips, they'll kind of touch their waist and sort of feel a bony thing, and they'll say, oh, that's my hips. And that's what they can feel, and that's typically what humans label in 2D data sets. They don't realize that the hip, that their femur curves inwards and the hip joint is quite a ways in. So if you're actually capturing the anatomical structure and the true centers of rotation, you're going to have something quite different. So this produces a difference between simple and 2D images. So if you're trying to either evaluate simple on this image or to train simple from this image, you need to address the fact that the hips don't match, and probably the other joints as well, right? But it's not just a problem with hand-labeled images. If you take a mocap data set, say you take human 3.6M or you take human EVA or one of the others, you're going to have joint locations computed by Vicon or OptiTrack or one of these things. And they may not correspond to your simple model either. So you're going to need a joint regressor if you want to train or test on such data sets. So that's the point I'm making here. There's an offset between where the actual joint is and where humans typically label the joint, or where a mocap system thinks the joint is. So Vasilis, you want to describe the regressors?
Yeah, so I guess now the million-dollar question is which joint regressor should I use when I train or test? So for example, again, we have a simple body and then we have different variations. So on the left, you have the basic, the normal simple joints. And then we have two variants of these 14 joint regressors that are used by some most popular models, let's say like HMR and SPIN. And you can see that even for these models, there's a difference. Like for example, look at the elbows between HMR and SPIN or at the hips. So there's a slight variation. So which one should I take? Which one should I use for my use case? Ideally, what you would want to do is to have a separate joint regressor per dataset, trained and adapted to address the biases in each of them. The problem is that you don't always have the data. So for example, if you just want to use a 2D key point dataset, then you don't have a mapping from 3D vertices to the joint, so you can't learn the intermediate. So in practice, what I think you should do is be consistent. So always use the same regressor that you use to train your model. You should use the same to test. And to illustrate this point, like below, I just computed some numbers. I took the pre-trained HMR model, the pre-trained SPIN model, and then ran them on 3DPW. But then I changed two things. So I changed the joint regressor that I used to generate the ground truth joints and the joint regressor that I apply on the model vertices to get the estimated joints. And as you see, for the same model, there's a relatively high variance. So this might not, this might prevent you from getting state of the art. So, worst, at least the least thing you should do is be consistent with your regressor. One other smart thing is you can look at Jana's hand paper, and I think that's also nice. What she did there is that she fine-tuned, like as she was fine-tuning her model on a specific dataset, she also fine-tuned the joint regressor to adapt to that dataset. But this is just a crutch, as Michael said, because we tend to, for example, 3DPW report is MPJPE, using a subset of the joints. But in reality, we don't want to evaluate a subset of imaginary joints. We want to evaluate the quality of the surface that we got. So if you have a data set that has surface information, so in the form of simple parameters, Simplex, or some other body model, if you want to evaluate joints, then use the actual simple. Since you predict simple, evaluate the predicted simple joints with the ground truth simple joints, evaluate the vertices with the ground truth vertices, and the same for Agora, where you have Simplex. So, to recap, least thing you can do, be consistent with your regressors. If you can, fine tune. And if you have simple or Simplex or model data as ground truth, use those. Don't use some arbitrary intermediate quantities to evaluate your model.
And this is so people weren't thinking, and so an HMR did the right thing because it had no way of testing on ground truth where it had the simple joints. But people then took that idea, they just took that regressor blindly and they applied it to 3DPW where they didn't need it at all. Right? If you're estimating a simple model and you have simple ground truth, you just compare and you care about the joints, fine, or the vertices, even better, which we call V to V for vertex to vertex error. But there was no reason ever to use a regressor on 3DPW if you were fitting a simple model. So that's unfortunate that happened, and now people all report that, and now I don't know how we get out of that situation.
So, Michael, we have a couple of questions that just came in.
Sure.
The first is, what's the recommended way to handle mismatch between rigs when we drive simple using 2D key points? Example, Coco.
Right, so you need, I think you need a regressor there between simple and Coco to properly drive it. I don't know if we have a trained one already online. Yeah, it's actually a little tough to train because hand labels are pretty inconsistent, and you have this whole rotation thing. So the right thing to do is to solve for the 3D translation of the joints in simple such that they project into the 2D images and minimize the 2D loss. That's the right thing to do. But if you don't have the right focal lengths and everything else is wrong, it's a bit messy, and when we've tried to do it, it doesn't actually produce that much.
The second question is, despite the simple joints versus human joint annotation difference, does it still work, and why in combination with OpenPose 2D joint detector?
That's a great question. So I think we had a picture of the OpenPose's joints, hip joints are also in the wrong place. I have seen results where that leads to the simple model having too narrow hips, because you've got, if you think of, or too wide hips, one or the other. Wide hips, because it's trying to match those joints. So does anyone have a good answer?
Yeah, I can try to take that. So what Michael said will happen. So for example, if you like the problematic joints are the hips and the neck. So if you look at the simpler hierarchy, the neck is, I don't know if you can see me around here. Like for OpenPose, if I remember correctly, the neck is essentially the midpoint between the two shoulders. So essentially what you have is a constant bias in height. So what will happen is that when you optimize or train to match this, the model will just try to inflate or increase the person in height, so to overcome it. So if you're okay with, like, your skeleton might look okay, but your surface might not. So one solution is to use a joint regressor. The other is to ignore those key points if you don't want to. Both have their advantages and disadvantages. So the joint regressor solution might not be ideal if it's not trained on Coco, because it might correspond to some other convention. Ignoring the joints means that you throw away information. So it's always, right now, it's always, there's not a clear best solution there, unfortunately.
Yeah, I mean, the long-term solution to this is having ground truth, having images with ground truth simple. And there's a bunch of efforts to do that. So Agora is one with synthetic data. Touches mimic the pose data set, also improves results on 3D PW, and that's in the wild, but high quality simple X ground truth. So I think pushing that is the long-term solution to this. And then, you know, if people want to use other body models with different joint locations and so on, then we just need to map between those. But I think once we have 3D body models, if the ground truth is all in 3D, mapping between different human body models shouldn't be a big deal.
So the last question is, how can we, what are the ways that we can quantitatively evaluate the surface of the models that are predicted?
Yeah, so we use V to V error. So that is if you have, so if your ground truth is simple and you're estimating simple, then you know you have correspondence. So you could just look at the vertices of the ground truth and the vertices of simple and compute the distance between them. Take the mean distance. That works pretty well. You might want to focus in on the hands or the face or subregions, depending on your particular problem. Now, if your meshes are of different topology, then you need a vertex to surface distance. So you need to find the closest point on the surface of the ground truth, which is relatively easy to do also. And I think we have code for that, if I'm not mistaken. So it's a point to surface distance.
One question, because I'm getting a bit confused. We see in this table 2 regressors, but the simple model itself has a joint regressor.
Right.
Are they applied in a different way? What is the input of these 2 types?
Great question.
I can take it. So thanks, Dimitris, for the pointer. I forgot to comment on that. So usually what people will do in the end for these 14 joints is you take the final post mesh, so simple after applying shape and shape length shapes and post deformations, and you have a simple linear regressor on top of the vertices. The internal, this is a different thing from the internal joint regressor of simple. The internal joint regressor of simple should not be replaced, should not be touched, should not be messed with. It's something that the model needs to correctly generate the surface. It was trained with this, so it expects this. You should not touch this, mess this, or change this at all.
So can I get a mesh that is articulated and apply the internal simple regressor on the post mesh? Yes or no?
No. Well, you can, but it's not trained that way. It's trained to regress in the T-pose, the correct joint locations.
All clear.
So once you pose the model with the with the pose correctives, that will move the vertices around. And I don't guarantee that you would get the same vertex positions as you would get if you started in the T-pose, regressed, and then articulated the model. Does that make sense? It actually scares me that people are applying a linear regressor to the posed model to then evaluate accuracy, because I don't understand why a linear regressor on the non-linearly posed vertices of the mesh it makes any sense. But that's what people are doing.
Yeah, that's all, Michael. So we can move on.
Let's go on to another one. Noreen, I want to use simple in Maya, but without dependency on NumPy.
This isn't really possible just yet. We're working on some way to do this. It's just about the libraries available inside of Maya, but Maya comes with its own Python, so it should by default, the most recent versions should have NumPy.
Okay.
Yeah.
Nima, how do I add soft tissue dynamics to Simple? Don't see very much this very often, maybe because people don't know that it's there or that they could do this.
So one can animate soft tissue dynamics of Simple with dimple parameters. Like dimples are like similar to any other parameter of Simple, e.g. like pose, betas, and for example, a mouse uses 8 dimple parameters to get more realistic bodies from sparse set of markers. And in the tutorial of a mouse, I have a code snippet showing how to use these dimple parameters to like articulate soft tissues further. So soft tissue, just to be clear, are fatty parts of the body. So you can expect a lot on the belly, on the thighs, on the chest. So for that, I'm going to go through this line of the code very fast. So line 45, the top one, I'm loading an Amas MPZ file. You can obtain it from the Amas website. And then I determine the gender because with this gender, I would need to load the proper body model, either simple H or simple. So Amas out of the box works, should be used only to articulate Simplex or simple. And then I need to get the appropriate dimple model. So this has the coefficients in. And then I specify how many betas and how many dimple parameters there should be. Like for Amas, we provide like Amas sequences in 16 betas and 8 dimple parameters. And then I get an instance of the body model from the, like, to interface the body model, I use the human body prior. So then I prepare the parameters in line 82. So I'm there. And then I move them to PyTorch. And then I pass them through the body model instance that I just obtained with dimples. So in line 184, you see the dimples at the end of the list. So these parameters are passed into the body model instance. And then I have the evaluated body model with dimples. And then I use the code to visualize it. Michael, if I have the next slide.
Yeah. Sorry. Yeah.
So here, I just ran it one time to produce these samples. So on the right, the body is without dimples, and on the left, the body is with dimples. So pay close attention to the belly area and the chest and the thighs. You should see more lively, dynamic soft tissue animation there.
It doesn't play very smoothly. It's kind of a weird playback, but I think maybe we get the idea. What if people don't want the dimples? Can they just ignore them?
Yes, they can be fully ignored.
Great. Thanks for that. Hopefully more people explore the soft tissue stuff. I think it's pretty neat. Yeah, Ahmed.
So whenever we have ambiguity about the gender of the subject, so this happens typically when we're regressing bodies in the wild. So we don't know whether they're female or male. We provide a gender neutral model for those use cases. What is a gender neutral model? A gender neutral model, its shape space is trained on male and female subjects. It's able to represent both genders better compared to just using a gendered model. We provide neutral models for simple, simple H, simple X, and star. If you would like to, for more information, we have under the Simple Central web page in the Simple Made Simple website, like we pointers to where to get each of those models. So Michael, can we go to the next slide? So now we provide, as of I think earlier this year, we provide the 300 shape components of Simple, Simple X, and Star. So initially when Simple was released, it was released with 10 shape components, 10 PCA components. You can definitely capture a lot more detail in body shape as you add more shape components. So we provide 300 components, which we know from our experiments is sufficient to capture all information about body shape, essentially. And this is available for Simple, Simplex, and Star. And again, for more details, those are all available to download today, like if you want. And you can find more information on the Simple Central website, webpage. That's all.
Super. Hey, Timo, I just want the face or hand vertices. That's really all I care about. How do I get them? I've got a simple model or Simplex model. I want to get the hands or the face out.
That's quite easy. Like Simplex was designed in a way that the flame vertices and the mono vertices are like real subsets of this mesh, as you can see here in like colored red, green, and blue. And we provide like vertex index lists of like the head and the hands on the Simplex website. And you can see here like some demo code that just indexes like the Simplex body with this index list and returns like the vertices in the Simplex mesh that correspond to mono and the flame body parts.
Fantastic. Sounds so easy.
It is.
Shashank, how do I get the joints out of Simple?
This is actually a really easy process thanks to the Simplex GitHub repository, which is linked here. And in this repository, if you go to the bodymodels.py file, you will find a simple class constructor, and you can create an object of this class. The only argument it takes is the path to the relevant simple model, which can be male, female, or a neutral model. And then it's just a matter of running the simple forward, where you provide the betas, the pose, and the global orientation, which you want the output mesh to be in. And then you could just get the joints and vertices like so. So it's just a 3-step process.
Fantastic. I guess we already heard about visualizing in Blender. Do you have something else to add there?
So in this slide, it just basically summarizes how, once you have the joints and vertices from the previous slide, how you can get that visualized in Blender. So you could use the TriMesh package. And again, you could create a TriMesh object, which takes the vertices, the faces. And then there's the function mesh.export, which just exports it as an OBJ. And then you can load the OBJ exported from this script and load it in Blender.
Fantastic. I want to create a skeleton. How do I get the kinematic tree in the joints?
Yeah, so the simple kinematic tree actually is the topology of joints, and it's a connected graph. So you need the joint indices and the connectivity between them. So this slide provides which index in the vector that comes out of simple joints corresponds to which part of the human body, which joint of the human body. And the next slide has the connectivity between these. So with these two, you could easily visualize the kinematic tree.
Fantastic, thanks. Now I want the parts of Simple so that I can train a segmentation method or something else. How do I get those?
It is pretty simple. So in the Meshcapade wiki, there is per vertex part segmentations for both Simplex and simple body models. So there you get for each vertex the corresponding body part label. And like using these segmentation masks, you can generate the above images using the code I linked here. So it basically just colors the vertices based on the parts.
Fantastic. Very easy. Hey, well, any questions? Do we have any questions coming along?
No, we don't.
All right.
Hold on, there is one about dimple actually that we haven't.
Okay.
I was just trying to type it. Can I regress soft tissue variations from pose variation? So essentially, this is the dimple model.
Yeah, that's a very good question. Right now, we don't have a model to do that. So there was an earlier paper called Dyna that did exactly that. We took the dynamic Faust data and we learned an autoregressive model that would predict the soft tissue parameters as a function of the motion of the body over time. And it worked pretty nicely. There were some neat tricks in there. The problem is we did it all before we made Simple. We did it based on an old scape model or Blendscape model. And all of that code has been deprecated, and we never went back and redid it for Simple and Dimple, unfortunately. So that would be a fun project to do that. It should be all trainable. As Nima said, the mass data set already includes 8 dimples, which is not very many, honestly, but it's just for mocap data. So one could do it even using a mass, or one could, we're going to release the simple fits to dynamic Faust. For some reason, we never did that. And then it would be easy to train such a model from that. It's a good question. Marilyn, I want to sample bodies. Can I do that? How do I get a random body?
Yes, so first, a precision about the shape space of the models. So as you said, they are defined by PCA. So we have a shape vector, which is stored in the betas attribute of the model. We also have the base vectors that build this shape space. Those are stored in the shape tiers attribute. And then a body shape can be written as a mean body shape plus a linear combination of those base vectors. And the norm of those base vectors is sigma I, which is a standard deviation of the training body shapes along this direction. So then to sample a shape, you just have to sample betas in a range of value from between -2 and 2. And that will give you body shapes that are plausible and lie in the range -2 sigma to sigma, where actually 95% of the training subject lie.
Okay, but we don't give people the sigmas.
So there are the norms of the BI, which are the base vectors. So those are in shape tiers.
Yes. So I think the point here is that we normalize the eigenvectors by the standard deviations so that all they have to do is sample betas in a, so that the variance is 0. Variance is 1 for each shape direction. So if they just sample a normal distribution, they can, with a unit variance along each direction, then they will get 1 standard deviation.
Yes.
And no, it's a little confusing that we did that, but that's what we did.
So then how do I use the shape prior as a loss? So when optimizing for the shape parameter vector betas, you want to keep beta values that are plausible. So for that, you can use L2 loss. But you should scale each dimension by its corresponding variance because of what Michael just explained. So it gives this loss that you can use for regularizing on betas.
Hold it, but we don't do that. We don't give people the sigmas. And because we've normalized it, we just use squared betas.
So often we tend to use only the L2 on the betas, yes. But I do think both make sense. And yeah, actually, we tend to more use directly L2 on betas, and also it's simple, more simple.
So we would have to release these sigmas to do it your way, which we haven't done. I don't know why. We could easily do that. Maybe we take that offline. That's an action item for us. I'm asking my own questions now. Thank you. Nima, I need a pose prior and I need it fast because I've only got 1 minute.
Sure, we provide vposer for that. So simple body pose prior. So for vposer provides simple body pose prior as the latent code of a variation autoencoder. So this vposer is trained on a mask and it provides an efficient code to represent the body pose of simple. So instead of optimizing for the real pose of the simple, we optimize for the vposer's latent space, and the decoder non-linearly maps to the valid human pose space. So if I have the next slide, please. So vposer provides encoding and decoding functionality. So in this code snippet, so we first load the vposer, we load the appropriate body model, and we get a sample from the mask. And then to encode from pose to POSE. So POSE is the latent space of the vposer. You just need to call the encode function of the vposer's model. And to decode it, you just use the decoder function. Here, as you see, I'm showing a code snippet from the full code tutorial of using vposer in this website on the left. So it may have the next slide. So vposer also can be used on top of being a prior. So as using the latent code as a prior and quadratic penalty on this latent code, we can use it to create new poses as well. So here I'm just randomly generating like 9 poses and visualizing with the tutorial code in human body priors like GitHub repo. So Michael may have the next slide.
That's it. We're out of time. Right, we're a little over time. So all these slides will be online. So we've got vposer, very nice. You can sample from it. You can interpolate poses in the latent space. We're going to talk about how you deal with different part rotation formats. I apologize. Interpenetration. There's a lot more to talk about. Why do I not get body shape when I estimate using Simplify? How do I get poses? Can I get the simple training data? How can I train my own simple model? Why is it so complicated evaluating data sets? So we will make all of this available. But right now, we need to move on to the next session. So thanks everybody in PS for working on that. I apologize to those of you we didn't get to. We can always record a little bit of extra later and put it online. I'm going to now